Here, we're going to look at the cylinder, take a cross-section in the middle of the cylinder, and plot the displacement contours over that cross-section. And we'll do that, we'll plot the displacements in a cylindrical coordinate system so that we can look at the circumferential displacement and the radial displacement. As we'll see, it's convenient to switch to a cylindrical coordinate system for this problem. Go to your ANSYS model, and if I look along X, okay, and I will turn off, for now, I will turn off the exaggeration of the deformation. In fact, I'll turn off the deformation. And if I look at the coordinate system, if I highlight coordinate system here, so right now I have only one coordinate system. And if I manipulate the view here, I have the XY plane. And if you want to make a cross-section, you have to cut the geometry using an XY plane. So what I need is an XY plane, not over here, but in the middle of the cross-section. And there are two ways to do this. If I go back to the previous view, I can just pick an entity. So if I have the face selection filter selected, select that outer lateral surface, and just say new coordinate, create coordinate system. And you see it always puts it, if you select a geometric entity, it always puts a coordinate system at the center of that geometric entity. There's another way to do it, and I will use that over here, so I'll just delete it. So here I'll just say new coordinate system without selecting a geometry, and then I will say defined by global coordinates, and then I'll offset it by half the length of the cylinder, which is 2.1 meters. So you see you effectively got that same coordinate system. And so let me rename that as offset coordinate system. Now I will go and create a surface by cutting through the model with that XY plane. So for that I have to go to model and select construction geometry, and then for construction geometry I'll select surface, and I'll say create that surface using my offset coordinate system. And then if I go, if I manipulate the view, I see it's going to cut the model through this plane, which is exactly what I want. And let me rename this as surface at Z over L, L being the length of the cylinder is 0.5. Now I want to plot the displacements over that cross section. So I'll highlight solution in the tree, and I'll say directional deformation. And instead of geometry, I will say surface, and then the surface that we just created. And so this is going to plot a U, which is what I want. So I'll just say evaluate all results. And then if I look along Z, and I can zoom in here using the right mouse button, and also translate. By the way, there's also, you can use this also to translate, pan. And you can see that plots U, and U is maximum over here, and the magnitude is maximum over here and here. Here it's positive, here it's negative. So in this case it's moving like that, in this case it's moving like that, and you can convince yourself that that's consistent with rigid body rotation. But really what I want to do is plot the displacement in a cylindrical coordinate system. So I'll go back to my coordinate system, and I will create a new coordinate system, and this time I will pick cylindrical, and I will say from global coordinates, and so I'll just have the origin of the global coordinates. And actually, can I go back to a previous view? I'll go back to that view. So now you should interpret So I have this new coordinate system, and you should interpret that when you're working with this coordinate system, you should interpret this as theta and x as r. So it's r theta z, theta being the cylindrical direction. And let me rename that. I like to rename things to keep things a little bit organized. So I'll call it cylindrical coordinate system. So now I'll go back to my directional deformation, and instead of plotting the component in the global coordinate system, I will do it in my cylindrical coordinate system. And in that coordinate system, I want it in the circumferential direction, which is y. So that should give me u theta. And so I will rename that as u theta over cross section. And then I'll say evaluate all results. And then if I go back to looking along z, okay, I see that the circumferential, in this direction, in the circumferential direction, there's no variation. But as I go along in the radial direction, it increases. And you can visualize this. So if I go to graph and I say play it, actually, I need to auto scale. To see it, I need to auto scale my deformation. So the deformations are really exaggerated. So you can see how the twist is happening. And this is, only the forward direction makes sense. It's just interpolating between the initial and final state. And I can also, and by the way, there seems a radial expansion here. And I think that's because of the exaggerated deformation. So we have to go and look at UR too, and let you do that and make sure that there is, and check the extent of the radial expansion. I can also probe the value. So let me turn off the deform shape. And I can turn off the mesh if I want to. I can say no wireframe, or I can plot the mesh. I'll keep let's say show elements. And then I can probe these values. So if I say probe, and I probe the value over there. So that should be equal to that's not what I wanted. So sorry about that. So that's u theta equal to beta times r, where r is the distance from the center to that point. So from here, and since you know r, you can back out theta, and that's true of any other point too. So this is one way you can get beta. You can get beta 2 at different points and see, oh, it's the same. So I'll let you do that. And then if I want to get rid of this label, it's not intuitive. You have to highlight label here, highlight it, and say delete. So by looking at u theta and ur, we already looked at the out of plane displacement, and we found that small. You can, check if the cross section is just undergoing rigid body rotation as assumed in the analytical solution. And you can say file, save project.